All right, guys, thank you for coming to the Policy at Macomb seminar. We're very grateful to have Panos Toulis here with us from Booth, the Statistics and Econometrics Department, and he's going to talk about a very interesting project that he worked on, I guess maybe about a year and a half or 2 years ago now. 2 years ago exactly, where he is looking at a very important problem. So I don't know if you guys remember, but early on in the pandemic, there was a question of, well, who actually has COVID? How prevalent is COVID? Panos is going to talk about it.
Yeah.
Thank you, Panos.
Yeah, thanks, David. Thanks everybody for showing up on that lovely sunny day. My name is Panos, and I'm going to, as David said, I'm going to use COVID as a motivation. But I'll try. This talk has two parts. One is talks about the COVID, like the specifics about the prevalence, but also gets into more theoretical, the theoretical aspects of inference. So I kind of put all that stuff in part B, which is a kind of a bonus. So we'll see if we get there. But okay, COVID prevalence was, it is, I guess it was more important back then, like two years ago, because it ties directly to the lethality of the disease, right? The case fatality rate, let's say. And it's important. It was important to understand prevalence because in April 2020, almost 2 years ago, there were numbers floating around that the fatality was, let's say, 5%, right? There was an official number published by the World Health Organization. But at the same time, nobody really believed that, and people thought that it's perhaps many cases were unreported, and so people were doing this the so-called serology studies, like serology tests, where basically take blood samples and they look for antibodies in response to COVID infection. Okay, and so the idea is that if I find in the population in these studies, if I find some people who have been exposed to COVID, and then kind of tally all the numbers together, then perhaps I get a more accurate number for the lethality of the disease. Now, 2 years ago, there were a lot of there's a flurry of activity in that area. Here are just three samples: one from Germany, the other from Netherlands, and then the U.S. And what I remember from those days was that the response to those studies was kind of mixed. Like first, it was given good news because it seemed that a substantial number of cases were unreported. Right, that was good news. It was not, that disease was not as fatal as people thought it was. But at the same time, these numbers, many of those numbers were pretty small, right? Like in the Santa Clara study, which I'm going to focus on, that number was from 2% to 4%. People wanted the hope that more population was exposed to COVID, but it wasn't. At the same time, there was heterogeneity, where perhaps like in New York or like in Germany, these numbers were much higher. So it's just, it kind of painted a complicated picture. Now, specifically about the Santa Clara study, it became quite controversial, and I don't remember if you, I don't know if you remember those days, those news, but here are just a couple of examples. So these are studies on top that basically announce the study results, and here are some of the more, let's say, negative reactions to that study. So it got heated like very quickly, it got political also, and up to the point that there were kind of some prominent voices calling for an apology from the authors of that study. And just for fun, let me test your media savviness. Which one of these headlines you think is coming from BuzzFeed? One headline here from BuzzFeed. Is there a pattern? What's that?
Maybe the bottom one.
Any other ideas? Good guess. Definitely dramatic.
No, the second one is from the New York Times.
This one here, it says, two antibody studies say that infections are more common than we think. Scientists are mad. It's like all the scientists are mad, of course. So the Andy Gelman is a famous statistician at the University of Columbia, has a very successful, very prolific blog, kind of posting about current events. And of course, back then, a lot of discussion was about that study and also about prevalence. And a lot of the criticism, the arguments were kind of discussed in that blog. So basically, the argument was the following: it said that look, if we look at the study, we kind of do the exact, calculate the exact binomial prevalence interval, we get a false positive rate for the test. I'll get to those numbers later. So we get a specific confidence interval, and then the point is that for the high end of that interval, it's perfectly plausible that the short-term prevalence rates published in the study are mostly or even entirely due to false positives. Okay, so basically the argument was that the data were consistent with the 0% even prevalence, right? Which means that all of the 50 positives that we got in that study were basically false positives. Then it makes a very interesting and very astute kind of observation here that the challenge is not about performing binomial model inference, right? Doing inference for proportions, but it's really combining multiple sources of uncertainty. And I'm going to focus on that part here. So this was a very, very, very excellent comment about the situation and about the challenges of that problem. But then goes on and says this famous or infamous statement that the authors owe us an apology because we wasted time and effort discussing this paper whose main selling point was a product of a statistical error. And that was quite bizarre to me because a lot of the arguments that come earlier were on point, very good, scientific, valid criticisms, but then it didn't really substantiate that strict, let's say, that harsh comment that we need an apology, right? There's nothing, I don't think that they had nothing to apologize for, and I think in hindsight it was the essence, the gist of that study was correct. And then goes on to vastly over institution as well, so let's just not get there. But all of that is, of course, in the blog post if you're interested to read that. Okay, so now it's a little strange, right? Like we live in 2022. I think we are pretty sophisticated in our tools. Like we have machine learning, we have deep learning, we have kind of advanced statistics, etc. How can we really have a debate? How can we screw up a problem where we only have a couple of proportions, right? To deal with. So it was really interesting from a pedagogical, let's say, perspective. Like how can we possibly screw that? Like how can we have controversy about that simple problem? So as I said, this talk is just two parts. The first part is kind of looks into that particular problem. I'm going to describe my approach to that problem, like what I did and why I think is better than the alternatives, at least in that simple problem. And then part B, if there's time, if there's interest, I can talk about other examples where I think this idea of what I call finite sample inference can really help you, can really kind of resolve some problems. And these other examples include name and Scott, the estimation of periodicity in astrophysics are pretty varied. So if we have time, we can happy to go there. But this is really the main part of the talk today. Okay, so for part A, I'll talk about the study itself. Talk about the controversy, like why did we really screw this up so bad? I will talk about the method that I propose and then show the results in the Santa Clara New York study. Okay, so Santa Clara study. Right, what happened there? So first of all, there were three studies really, and it's a little more complicated because there were actually two papers. One in early April, then the other was like 3 weeks later, and they used different sources of data, so it's a little complicated. I think what I present here is mostly based on that second paper. The main study was really the study where they took 3,330 samples. They kind of tested through some tests like antibody testing device, and then they found 50 positives. Okay. Of course, the problem is that we don't really know if these positives are true or not. That can be part of the problem. But if you take these numbers at face value, the point estimate for prevalence is 1.5%. Okay, all right. Just divide 50 by that total number of trials, and that's it. Okay. However, your testing device is not perfect. If the testing device was perfect, then we could take that number, produce an interval, and then we just go back to business. But that's not the end of the story, because the device is not perfect. Like even when you have the COVID, you can still not find COVID. If you don't have COVID, it can still find COVID. Okay. So in order to deal with that, we kind of did two smart things. One was we had one calibration study where you take pre-COVID, like pre-2019 blood samples. We know COVID didn't exist back then, and you pass it through your device. And they did this in 401 samples, and they found 2 positives. Now, you know that these are false positives, right? Because you know that these blood samples are earlier than 2018. So that gives you an estimate for the false positive rate of your machine. It's 0.5%. In the second calibration study, what they did, they took blood samples from people who actually were infected with COVID. So these were true positives. They found out of the 197 tried samples, they found 178 positives. And now you know that these are true positives. Okay? And so that gives you an estimate for the true positive rate, which was 90.35% for that in that sample. Okay. However, the problem is here that we want to estimate the prevalence in the main study, right? From this 50, how many can we possibly, what is the actual number of the true positives in that main study, okay? And we use the calibration studies as additional source of information about the test performance characteristics, okay? So in some sense, we need the calibration studies to inform us about the performance characteristics of our testing device, and then we have to use that in order to do inference for prevalence, which is our main parameter, the main target of inference here, the parameter of interest. So, but overall, it looks very simple, right? These are binomials. That's statistics 101. Like, how can we possibly, how can this possibly be complicated? But it turns out it is. It's actually quite challenging, quite complicated. That's exactly what Gelman was kind of trying to say in that quote, in that post. That the challenge here is, how do you take those hats, from the raw estimates, from the false positive estimates, the true positive estimates, how do you take all that uncertainty and propagate it into your final estimate for prevalence? Okay? This propagate is also a verb that the original authors used. Like, how do you propagate that uncertainty to your parameter of interest? So what did Ben David et al. Do in that original Stanford, the Santa Clara study? Well, first of all, they kind of wrote down, I think they pretty much did what everybody will do. They kind of wrote down the base rule. So assuming some false positive rate, true positive rates, what is the equation that gives me the final prevalence? Okay? And if you do, it's very simple algebra, you get an expression like this. So this is the final expression. Now think about the expression that they started with was the population version of that. So that was the true prevalence here, despite this FPR was actually the true false positive rate. And then they said, okay, let me now take that estimating equation and plug in my sample values. Okay? And that gives that this equation 1 gives them an estimator. Okay? So now you have an expression about, so this gives you a point estimate for your prevalence, like what you're trying to figure out. But here also where the problem starts. What is the problem? Well, the problem is now that there are a bunch of hats involved in that estimation. Okay? It's not a direct proportion. A bunch of hats here, and somehow you have to, in some way, you have to propagate the uncertainty of those hats into your final hat, right? Your parameter of interest. How can you do that? Well, in version 1 of the paper, what they did was to use a delta method. They said, okay, let me assume that these things are have some variance, then I use the delta method, and then I will get some variance for that by hat. Well, the problem is that here that the delta method requires normal approximation. Okay, and in order to do that, they basically use the normal approximation formulas for these individual hats here, for the P hat and the Q hat, the false positive rates and the true positive rates. Okay? But this is really bad idea. And I'm not criticizing the authors, I'm criticizing our profession really, because the normal approximation, it's a 100-year-old idea. They did it because we didn't have computers to calculate confidence intervals. We don't need it right now. Right now we have methods that actually exactly can calculate for you an exact confidence interval without normal approximations or anything like that. One of them is the so-called Clara-Pearson confidence interval. It's an exact confidence interval, works for any n, and does not assume normality also. So it's really, really bad idea in our textbooks to have that. We can still have it, but not have it as our main thing that we teach about estimating proportions, right? That's also even worse when we have very small proportions, which is the case here. Now, even though there are exact methods in binomial inference, like the Clara-Pearson and the confidence interval, they don't extend to one directly. Like there's no theory. It's not like if you're also a practitioner, even a statistician, you cannot really take that and then be able to compute an exact interval for a complicated point like that. we can do this individually for the p hat, the q hat, but not for that entire operation, right? This entire formula. And I would say that this is really the main methodological contribution of that of my paper is really to propose a general method to do not exact but finite sample value inference, even when you have this complicated quantities, like these complicated hat equations. All right, I'll get to that a little bit later. Now, the authors got a lot of pushback on that, which is understandable. So that's why in version 2 they tried something different. They tried a so-called non-parametric percentile bootstrap. Essentially, they bootstrap separately the calibration studies, and then they cluster bootstrap the main study, and then kind of produce some intervals based on them. What's the problem? Well, I don't know what conditions guarantee validity for bootstrap. Right? Bootstrap is also asymptotic, right? It works with n goes to infinity. So it's not really clear what happens for a finite n. Moreover, and what's even more concerning, people did other forms of bootstrap. Actually, we say bootstrap, right? But it's really, there are a million different bootstraps out there. And in that particular problem, other researchers did a very different bootstrap and they got very different results, basically. That tells you that we just put a lot of burden into practitioners. We say bootstrap, but there are so many degrees of freedom. There are how many different ways of doing bootstrap, right? I don't even know what percent that bootstrap is. I have to look it up, and I've been working on this resampling in that area for quite some time. I think, but then what's even more of a problem here is something that I didn't tell you beforehand, is that this equation 1 is an approximation. It's not a really valid estimate in all settings. In the sense that, for instance, it works only when this thing is positive, right? And it has to be between 0 and 1. This is the only case, the settings where there are specific settings where this equation makes sense. And the authors actually say that. They say, let me assume that this thing is positive, this is positive, then you get the estimating expression. Okay? But the moment you put it out like that, essentially you exclude cases where pi is 0. Right? But if you take that estimator at face value, this can give you 0, can give you negative prevalence rates. This is completely invalid. Okay, so even when you do bootstrap here, it still works with an estimating equation that can be valid. It's not really valid in all settings. So trusting all inference on that estimating equation 1, I think, was the original scene of that thing. Okay, and I think this was also the criticism coming from Gelman and others. But again, this is not a criticism to the authors for me. It's more a criticism to the profession, really. So if you teach delta method and other things that are just not, or the bootstrap, which are just, I think are ambiguous, first of all, and also they require a lot of work for a practitioner, like taking derivatives, kind of using normal approximations. It's just not, I don't know. You'll see that I'm going to argue that this is really not necessary, at least in this simple case. Okay, so what else can we do? Of course, we can do a Bayesian approach, and where one can put some priors and then look at the posterior about prevalence, and we get something that's definitely kind of makes more sense, at least compared to those cases where you get invalid estimates from the previous approach. This figure from Gelman and Carpenter 2020 shows that 0 is in that posterior distribution, even though it's not really at the center, right? You can see that the center of that posterior is more closer to 1%. However, still that approach, I think, for me, has a lot of degrees of freedom, especially for non-trained practitioners, right? Because what? Think about it. You have to specify the priors. And specify, you need to understand the nature of the problem. You need to specify some well-suited priors on your hyperparameters. You have to do posterior sampling. Perhaps you have to use some complex software like STAN. So there are many degrees of freedom involved here that I think there are a lot of burden for people who are not just we're kind of asking a lot of things from like researchers, like practitioners who just don't have that statistical training. For Gelman and Carpenter, of course, it was easy, right? But these are world experts in Bayesian inference, so it was easy to come up. You see this log normal priors, etc., and be able to do all the diagnostics and the heuristics that are required. But I don't think it's accessible to everybody. There are other problems within the Bayesian inference, more fundamental, that have to do with models that are not well identified. I'll talk about that later because it gets into the theory of inference, which is perhaps not, it's kind of a heavier subject, I guess. All right, so fine. So more or less now, what I've said is that we start with this simple problem. There are only really three proportions that we want to estimate: true positive rate, false positive rate, prevalence. And what people used was either bootstrap or the delta method or the Bayesian approach. All of them gave different answers, sometimes for the same method, like the bootstrap, right? Because they use different variants. The delta method required from these doctors to take derivatives, right, and then do normal approximations, etc. So at some point, my reaction was, can we really expect scientists to be able to do all that, right? And actually, Ben David et al. Didn't do the delta method. They didn't do it correctly also, right? That's another funny aspect of that story. And that's not the problem with the authors again. It's a problem that we have these tools that have so many degrees of freedom, and we tell them, look, here's a very simple problem, try to apply it, and it's not totally straightforward. So I think our failure was collective. Our text still fits what I think are outdated formulas, like the normal approximations, which is completely unacceptable, I think, in the 21st century, right? Like, it makes sense when you don't have computers around and you want to calculate things fast with the pencil and paper, but not anymore. Frequently, bootstrap or Bayes, these are the standard, what we say is the standard methods of doing inference, pick your favorite. Still, they can have too many degrees of freedom, I think. Either bootstrap or Bayes, if you think about it, there are many different bootstraps and many different ways you can do for any given problem. And I think that many degrees of freedom is detrimental to it puts a lot of cognitive burden to researchers and scientists to do their job. There are additional problems when the model has irregularities, and that's something, again, that gets into the theory. If we have time, we'll get to that later. So ultimately, my point is this. I'm saying that there is an area of statistical problems where we don't have to do frequencies or Bayes. There's a third approach where you can do something like, for an approach that is conceptually simple. It's a very simple method, as you're going to see. It can work with complex scenarios, and also can be valid in finite samples. But also at the same time, it's unambiguous in the sense that there's just one method of it. There's no calibration that you have to do or any hyperparameter tuning that you have to do. Okay, so this method is coming up. We'll see that it's extremely simple, and I think it's very simple to teach it to practitioners. Okay. Of course, there's a caveat. I'm not saying that everything we've done so far is wrong, clearly, right? The computation is the main bottleneck of that approach, and of course cannot work. You'll see that I'm going to argue that cannot work well beyond, let's say, 10-dimensional problems. But in this case, where I have just three parameters that I want to do inference on, it really can be the preferable approach. So I'll try to make that argument. Hopefully, I can convince you. Okay, so let me try to explain now what this final. Really quick, I think, and hopefully conceptually clear. Okay, so let me summarize the model again, so that everybody is on board. What is our data? Our data is just three numbers. Okay, the positive results in the calibration 1 study, positive results in calibration 2, the positive results in the main study. Okay, and in the calibration 1, we know that these are false positives. These are 2 here. 178 were true positives, and then 50 were just unknown. These are positives, but we don't really know. It's a combination, perhaps. It's a mixture of true positives and false positives, potentially. What is our model? Our model is a simple binomial. This is where everybody agrees, I think, that everybody, either based on frequencies or whatever, we kind of agreed that the binomial model makes sense here, where we set we have a testing device that has a probability of giving a false positive with a probability P of giving a false positive, probability Q of giving a true positive, and then let's call pi the true prevalence. Okay? These are the unknown parameters. So I can collect all of them in one vector. This is my theta, and I want to do inference of that on that vector, mainly on that pi. And what is my data? My data is this capital S, which are really the positives in these three studies. Okay? Extremely simple problem, and still we have a lot of controversy for months while facing an existential threat. Right? When humanity was facing an existential threat, we were still debating a simple three-dimensional molecule. But you'll see that it's quite subtle. Okay, so theta is going to be my three-dimensional parameter with the unknown test performance characteristics and the unknown prevalence, and S is going to be my observed data. Okay, it's the positives in all those steps. Now, one thing again that everybody agreed on is that when we posit this binomial model, then we can calculate that density exactly. Okay, it's a simple exercise, really. So what do? This density is, and of course, and if you assume independence, then it's a binomial density for the calibration 1, is a binomial density for the calibration 2, and this is the case where I know these are true positives, false positives, and this is the case here. This is the summation here. This is the main study, and the main study is a mixture of binomials. Why? Because this number 50. It could be a combination of false positives and true positives, right? There is a chance that all of them are false positives. So this 50 number that I got could be 50 false positives and 0 true positives, or it could be 49 false positives and 1 true positive, okay? Or 48 false positives and 2 true positives. So they have to sum up to 50. So I know what they sum up to. I know they sum up to 50 positives because I observed the data. I just don't know the composition. But this is very easily, you can do it on a computer, right? These are just binomial densities, essentially. A mixture, and then you have the other two calibration steps. That's basically, okay? So the bottom line here is that the moment we pose that simple binomial model, we can actually calculate its full density. If you tell me some model parameter, some parameter values, these thetas, and then you tell me what you observed as positives, I can tell you exactly what that density is. That's the baseline. Now, in the sample, we observed 2 positives, false positives, 178 true positives, and then 50 positives in the main study. Okay, these were the observed data in the Santa Clara study, essentially. So now the question is the following: what can we say? We have this observed data. What can we say about theta 0? Some potential values of my unknown parameters. Just as an example, let me make this a little bit more concrete. Suppose somebody tells us, look, I'm only interested in this combination of parameters. 1.5% false positive rate, 90% true positive rate, and then 0% prevalence. Suppose I'm interested only in that combination. Can you tell me, the question is this, can you tell me if the data agree to that assumption, can you tell me if these parameter values are consistent with the data? Okay, so how can we solve that question? Well, here's just one kind of a visual representation of that density, just to get you a visual idea into that problem. So that start here is the observed. These are the observed data, and this is the density of my statistic. Okay, and it's kind of reduced it into being two-dimensional. I think I keep one-dimensional fixed here. The point here is that for this theta naught, theta 0, for this particular combination of parameters, what I observe here is not really at the peak. It's not the most likely value of data, right? The data that I expect to, the data are kind of here at that peak. Okay. So the decision is this: like, even though I didn't observe that my observed positives were not in that peak, but they were over here in that tail, how can I decide whether the theta 0 is false? Okay. That's the fundamental question that we have to answer first. And if you were a frequentist, you might say, okay, what I will do, a frequentist essentially takes the likelihood value for the observed data at theta 0, and essentially compares it to the likelihood value of the end rate, of the argmax estimator. Okay, the one that maximizes the likelihood. That's just what we're doing it. Bayesians will just do something very similar, but kind of weight this by with the prior. Okay. One underlying assumption with both of these approaches is that the likelihood function, this density, this fs of theta, has some nice regularity properties. Again, this goes back to theory. I'll discuss that later. So let me kind of tell you how you can do this without kind of making those underlying, these implicit regularity assumptions. So what I propose is the following to answer that question. But let's treat this as a hypothesis test. Okay, let's answer, kind of try to test the hypothesis that the true parameters are equal to these numbers, 1.5%, 90%, and 0%. Okay, so let's just treat this very simple test. Now, because a hypothesis test, we need a test statistic. So for a test statistic, the statistic is one that if the null hypothesis is true, it's going to take some atypical values, right? Or let's say higher values than you would expect. If the null hypothesis is not correct. Okay, so clearly one idea here is to just take the density as your test statistic. Okay, so even though we have a three-dimensional parameter, even though we have a three-dimensional statistic, the density is a one-dimensional object. Okay, and also it's a reasonable choice because if the null hypothesis is true, you expect to see higher value, right? In this case, you could take the negative and kind of reverse that. It doesn't really matter as long as you make that comparison and you're consistent with that comparison. And here's the scheme, right? If T obs is the observed value of my density, then I'm going to reject the null if the probability of observing the probability of my test statistic is the probability that I get at most the T obs value in my density is less or equal to 12. Okay? Essentially, just intuitively what this test is doing is basically doing the following. In this question, whether theta 0 is plausible or not, it says, what is the density here? Let's say it's 10 minus 3, or 3 to 10 to the minus 3, just some value, okay? Then it slices that multidimensional density at that same level, and then looks how much density is below that level. So imagine here a slice around, at this S obs level, at the observed value of the density, and then think about how much mass there is below that. If that mass is less than alpha, then we reject the null. If there's more mass than alpha, it means that this value of density is not really atypical, right? So we don't reject. It's that simple. So basically, looks for the mass below that level. The proof is elementary. Why I think this thing works, because if you look at that, this is basically the this probability of less or equal P obs. That's basically the CDF of T, and T and T obs have the same distribution. That's a uniform, and so you get that expression because of the uniform. Okay, so just one line for if you assume continuity. Like if you have a discrete sample space, then you need one or two more lines. It's really elementary. Okay, so now we have a test for that null hypothesis. How can we build a confidence interval? How can we do inference? Well, we do the so-called test inversion, which essentially says, let me check all possible combinations of false positive rates, true positive rate prevalence, and then repeat that same test again and again and again for every different value of theta. Okay? So for every possible value of theta, what do? I calculate that density, find what the observed density is for the observed data, slice it, and then look into how mass is below. Okay? And if there is more mass than alpha below that level, I'm going to take that value parameters and put it into my confidence set, this theta hat. Okay, and this is the ultimate product of my proposal here, proposed method. It gives you a confidence set. Not necessarily a confidence interval. It's a confidence set. It's a confidence set because, as the theorem suggests here, it's going to cover the true parameter with the desired probability. Okay. What is the notable thing here, of course, is that this coverage probability holds for any finite n, and this is why I call it a finite sample valid method. It's a method that is valid. It gives you that nominal. It covers at the nominal level for any finite n. It's not asymptotic as bootstrap is or as standard inference is. Okay. It generally recovers, but in the case for the prevalence problem, is really that overcover is not really like that. You can actually plug in some numbers to show that this overcover is quite mild, 0.01. So it doesn't really change the probability of that. Okay. So I want to focus your attention here on that claim that this holds for any finite n, and this is what I call a finite sample inference method. It's a method that the claim is for any finite n. 5, 10, 20, whatever that is. Moreover, that claim here is, I didn't assume anything more than the binomial model. Okay? I didn't assume that things are normal. I didn't make an approximation. I didn't say, oh, let me assume this is only the 2 moments matter. No, this is just plain. It's a pure statistical method where the guarantee that you get depends only on this original binomial model that we set up. Okay. And I should also say that there's nothing specific about the COVID problem here. As long as you're able to calculate the density of your statistic, whatever that statistic is, it doesn't even have to be the sufficient statistic or the complete sufficient statistic or anything. Any statistic that you take is going to have a density according to your model parameters. Okay, and so that method can, if you can calculate that density, you pass it through that method because it's the only thing that this method requires. Right? You can see that here it's extremely simple. Right? Take every parameter value, calculate that density, look into calculate the observed value of the density, and look into the density mass below. Okay, and that's it. Kind of, it's a much more general method. So if you are able to calculate that density, then the rest is just brute force calculation, just plain computation. Of course, that's the main downside of the method, because you can see that here you have to do that for every parameter value, and you also have to calculate the density across your sample space here. And so if the sample, the statistic, the data statistics space. So if this data statistics space and the parameter spaces are big, then you can easily have major computational issues. However, in this case here, where we have 3-dimensional objects, it's pretty simple. Okay? Very straightforward. And you buy finite sample validity, just as easy. Okay. So as I said, this is a general method. It directly competes, if you will, with the more standard asymptotic methods of doing inference. So this is in part B of my talk. So what I want to do now is kind of show you what you get in the COVID prevalence studies, and then perhaps I would kind of walk you through some other examples from statistics and to show you the broader impact of that idea, perhaps. Okay, so here's what we get. Like at the end of the day, this is really the object that we're calculating, that theta hat, the confidence set. And because you see here, this is 3-dimensional, because it's a confidence set for the false positive rate, the true positive rate, and the unknown prevalence. Okay, it's a 3-dimensional object. So in order to visualize it, we split it into 2 graphs, right? Where on the x-axis here, I put the prevalence, the pi component, and here I put the false positive rate, the other the q parameter, and then another graph where I put the prevalence and then true positive rate, like the first component of my theta. And this shaded area is basically the confidence set. So every point here in that shaded area cannot be rejected at 5% level. In other words, every point in here is consistent with the data from that study, from the Santa Clara study. Okay, so what do we see? First of all, we see that if you see prevalence 0 here, we kind of look and see here that there is a shaded area in that 0 prevalence, which means that there are combinations of my parameters where 0% prevalence agrees with the data. Okay, that's observation number 1. However, you see that also you can see from that plot that it happens for false positive rates that are kind of roughly near the 1.5% level, and that's probably too high. This 0.5% level, this is what the authors estimated for their device. Okay, and that's, you can see that dashed line over here. So if you believe that that estimate is 0.5%, if you really think that, well, my device is at 0.5%, if you're really confident about that, then you can trace that line over here, and then you can kind of look into that shaded area on that level. You can see that if you make that assumption, then the prevalence rate goes from ranges from 0.7% to 1.5%. Okay, so you can make these judgment calls now. Like we have this entire theta, this big confidence set, and now you can kind of make some claims. And something else I did in that paper, I don't have it here, is that I looked at that point, at that same time, the FDA published, I think, a study for the performance characteristics of about 10 to 15 testing kits. And then I kind of argued that, used that study to argue why this 0.5% false positive rate is actually quite reasonable estimate. So that's why at that point I said, well, it's based on what we know. This, even though the 0% prevalence is consistent with the data, I think we can use some additional information from outside to really, and including that FDA study, to kind of argue that the prevalence is more likely to be around that. It's more plausible that prevalence is around that area. And that was massive at that point because, not what I said, but in the data study, because the prevalence was, if it was 1% in Santa Clara, that meant that the fatality rate was, if it was 2%, which was the original claim, the fatality rate was 0.2% instead of 5%. It's a drastic reduction, right? Now, if the prevalence was 1% instead of 2, as the author suggested, then the fatality would be 0.4%, like double that. And actually, right now, if we assume that everybody has gotten COVID, this is roughly where the fatality rate stands, around that value. Of course, there's more way to go, and of course, all of this is now superseded perhaps by different variants and other things, right? Other developments. So now it's too late to make this comparison. But I think the gist of that study was correct, that it was not as lethal as people scared that this disease would be. Of course, still we had 1 million deaths in the U.S. That's a massive number, right? So some portion, of course, was definitely kind of exercising some portion, at least in the beginning. Okay, so what I'm claiming here is the following: that's look, and what should you trust what I'm doing here compared to the Bayesian approach or the booster approach, right? Because this method I presented, there's only one version of it, right? There's no many ways of doing that. It's just that's it. Like you kind of calculate the density, and then everything is basically algorithmic, mechanistic after that. There are no multiple versions of that method. Okay, and that's number one. Two, I think it's pretty straightforward, right? To explain to someone, I don't have to talk about the philosophy of difference, right? I don't have to talk about trials or asymptotic analysis and things like that. The only thing I have to say is, look, here's the density of your data. Here's where you are. If you then we're going to argue about whether the parameter value is plausible or not based on what density you observe, and then what's the overall density of your data. Okay, that's basically. I think it's a much simpler method, right? You see that really the description of that method is light, and the proof is just one line. Of course, I'm able to do this because I only have to work with 3 parameters. Okay? In general, this can be practical. If I have time, I can talk about that as well. I don't want to overclaim here, but what I'm saying here is this is one application that is crucial. Right? We want to have finite sample validity is definitely preferable, and where finite sample validity is actually attainable. Right? You can actually do that, and there's only one version of that method. There's no different versions of that. So I think these 2 qualities are actually can be quite important. And the other is simplicity, of course. And you also don't need a package, right? Like this is the kind of coding this up is actually a very simple exercise as well. You only need to be able to calculate that binomial. Okay, so this is the New York study. Actually, much better results there, much more optimistic results we got from there, where the prevalence, you see that it's no longer 0%. If you remember that New York study was a study of different grocery stores, again, 2 years ago, and showed that the prevalence was between 13% to 16%. If you're willing to assume a smaller false positive rate, then it increased to 14% to 16, 17%. So New York got much bigger exposure earlier in the pandemic. Okay, and you can see that in the numbers as well. So what was evident back then was that also the COVID exposure was highly heterogeneous. Okay? And this was a very clear early signal that we shouldn't try to do universal policies. Okay, I believe that at one point, I believe it now. Kind of trying to accommodate this vast country with highly heterogeneous, right, in terms of exposure, in terms of population, etc., and try to cover everything with the universal policy was doomed to fail. And I think the U.S. did well in general overall because thanks to the independence of states and kind of tried different ideas and kind of saw what was working and what was not. Okay. So yeah, so that's basically it really. These are the kind of presented the method. This were the results. I guess I can take a break now if there are any questions. Perhaps I spoke too much. As I said, there's a bonus part B here that kind of takes that method and it goes kind of compares it to the Bayesian, to the frequent list, kind of pulls up examples, other examples from statistical inference. So if there's time, if there's interest, I can get to that. But this is really what I wanted to cover today. So I can take a break. If there are questions, I'm happy to take them now. If not, I can just walk you through some other examples.
So how did going back to the Santa Clara study, how did your confidence interval compare to Gellman's? What did Gellman say in that 2020 paper?
Yeah, I think Gellman's paper was on the version 2 of the paper. Like, version 2 had different data from version 1. And I think he's, wait a minute, no. It's possible that I don't remember this exactly. It's possible that this was actually from version 1 of the paper. In version 2, I think I got the confidence interval from for prevalence from 0.4% to 1.something%. So I didn't really follow like how his opinions evolved about the study, but I think he got most of it correct, like the challenge and everything. I just don't think that it was the there were no like statistical errors in the strict sense in that study. Right? It was just they kind of used to the best of their ability. They used whatever they had available, right? Whatever tool they had available. The Delta method, research.
Okay, my second question is this might kind of move us into the second part is. So the main criticism of this finite-sample method is that, well, I'd like to make a statement about population, about the population of Santa Clara, about the population of New York, about the U.S. population, whatever. And I'm kind of strongly relying on the fact that I just have this sample, right?
Yeah.
What would be your response to that?
Yeah, I'm more of the This is really the most important criticism for this finite-sample methods. And I would say that me and myself, I'm perfectly fine restricting my claims on the sample. I understand that you want to say something about the general population, but if you want to say something about the general population, maybe you do a more general population study, right? So I can see the value of trying to extrapolate, but at the same time, I'm much more comfortable saying something that's valid for whatever restricted, in any restricted sense, but at least it's valid in that restricted sense. Otherwise, I think you have to extrapolate, you have to make assumptions, and then I don't like, but I also understand that's a personal, it's a personal preference.
Yeah. David asked, did you apply to any other like studies related to like the proportion, or only this one in Santa Clara?
I think Santa Clara, the New York. I also have in the paper.
Okay, other studies.
Los Angeles one. Yeah. And I have an example also about the vaccine study. I don't have the details, but if you're the Pfizer study about the vaccine efficacy, that's another example of that idea. It's the same setting where you only have, actually in this case, you have two parameters that you care about. So I can talk about that. The point being, of course, that you can apply this when you have very few parameters, right? Which is the case in medical studies, I would say. Usually you care about those proportions mostly. You don't have, you don't deal with the variability.
And the bottleneck is like calculating the density. That bottleneck?
The bottleneck, that can be one bottleneck.
If you have like two main parameters.
Yeah, so here's one bottleneck, right? The fact that I have to scan the entire parameter space.
Right.
So
it would be kind of a simplex. Kind of like.
Yes, exactly.
Okay.
Yeah, and this increases exponentially with the number of parameters. The same can be told for the density, right? Like if this is the density here, you see that you have to sum up across all possible combinations. So now Here I have only 3 parameters, so it's doable, like not parameters, 3 statistics.
Okay.
But if you have more, then you might have to, right, kind of do more complex calculations. So there is a saving. There are tricks here. So the fact that you have to do this, you can do this separately. Like for every possible parameter value, you can do this separately, completely separately from all the others. So this is what we call empirically parallelizable as a problem. You can kind of throw it in a cluster, which is what I did. But I'm not going to sugarcoat this. This is really the main problem. Essentially, we're trading off finite sample validity, which is brute computation. So if computation is cheap, then I would argue for that. If you can do this, I would say that this is really preferable over the standard approaches. But you can clearly see that it can become impractical. That's not line.
And so on.
Yeah.
You did like kind of binomial. Can you extend it like to binomials? That's other categories or
Yeah.
Yeah.
As long as you can calculate this density, there's nothing special. Yeah, there's nothing special about the binomial.
Okay.
As long as you can calculate that density,
Okay.
then the test uses, it's really the test is using the density. Yeah, it doesn't, as long as you can scan then the parameter space and do all these calculations, then you're good to go. Here's binomial, it's convenient, right? You can understand that it's just binomial trials. It's just, it's into a stroke false. Yeah. But this could be multinomial, it could be something else. Actually, I can show you some more examples. Perhaps it's a good segue if there are no other questions. I'm going to skip that. Yeah. So here's one example where you have suppose you have data that are normal, right? You're trying to estimate the mean of that normal distribution, and your S here is the sample mean of your observations. Then in this case, your density is going to be the simple standard normal density, right? Because you know that the average of the y is also normal. So in this case, it's regular, it's nice. So you can just pass it now through this finite sample method. There's nothing that stops you from doing that. And if you do that, actually you're going to get something that's almost completely equivalent to the standard asymptotic plus minus asymptotic inference, right? And this is an example about the regularities. So here's another model now, where your mean is theta star squared. Now clearly theta star cannot be identified. You can identify it after the sign. You cannot distinguish between the mean being -3 or 3, right? So okay, this is a case of irregularity in your model, right? If you plot the likelihood, it's going to have 2 equal modes, one on the minus and one on the plus side. Now, what do you do as a prevalence? You know, delta method, perhaps. I would have to look it up, and I spent 6 years in the PhD as a PhD, right? I'm studying these things. I would have to look up how to do inference on theta star. I will have to take derivatives. Hopefully, I'm not screwing it up, right? Benedict et al. Did it wrong, that delta method, and I don't blame them, right? It's tricky, right? You have an irregular likelihood, and you have to be careful about this transformation. Like, how do you do inference? Well, again, your density here is you can easily calculate it. It's just you can use theta squared here, basically, and then you pass it again through that algorithm, the procedure. What you get out of it is just 2 confidence intervals. This is your confidence set now. One is centered at the negative values, the other at the positive values. It's as simple as that. Right? So the point here is to show that when the likelihood is regular, then you're fine doing the asymptotic methods, like the frequentist methods. And the frequentist method and what I'm doing, I'm going to agree more or less. If the likelihood is not regular, then what I propose is going to stay valid because it's provably valid. The standard method requires adjustments, and this is, I think, really why I think we should blame ourselves as statisticians, because we kind of start with these normal theorems, approximations, and everything, and forget to think statistically, right? What is a statistical problem? And then, of course, people like doctors and practitioners, the moment they have a complex problem like this one here, where you have multiple hats playing around, of course they're going to screw it up, because we will screw it up ourselves. So that's one. Here's another famous example. If you've done like some statistical training, you probably have seen that this name and score parameters. That's actually quite interesting because in this problem you have data, normal data with mean alpha I, another mean alpha I. You're trying to estimate the variance. The means here are completely unknown. Is alpha I. For every data point, the mean is unknown. Now, if you try to do the MLE here, the MLE is equal to that quantity. And famously, that MLE is inconsistent. The expectation of that is half of the true value. Why this is happening is the so-called incidental parameters problem, right? You have n observations, but you also have n unknowns. These are the alpha i's. You pay the price of that MLE. Okay? This is the so-called Neyman score parameters, the fact that your MLE is like completely biased and also in the and has also been used to advocate for Bayesian methods, right? You can follow a Bayesian approach and kind of resolve that paradox, but the MLE completely fails. Can you pass it through that method, this finite sample method? You can. Just notice that what you're doing here, this sigma hat squared, is just a statistic, is S, just like any other statistic. Can you tell something about its density? Yes. Given theta is follows a chi-square density. Just pass it through that procedure, it will give you this type of Converse symbol. That's exact. That's an exact Converse symbol. It's not even asymptotic. It's actually exact. So there's no paradox here. No paradox at all. It's only a failure of our assumption, the implicit assumption, our expectation that your MLE, whatever you optimize, your argmax estimator, the MLE, whatnot, has good properties. Which is completely unfounded. Like even in textbooks, you'll see that the assumptions like separability and things like that, they're totally varied and mostly assumed in faith. Like you kind of assume that this latitude is going to be regular. We assume that in the limit of all the data, of more data, we're going to get, the peak is going to be on the true value. But this is only an assumption, it's completely untestable, really. It's just mostly we take it in faith. And so the point is that your statistic is not immediately supposed to work well. Even when you optimize your machine learning try like doing that, right? They kind of take the data, optimize something, and then they say this has to work. No, not necessarily. Okay. And I have a comment here about fiducial inference, not so interesting. Let me pass the. Okay, yeah, I think these are the 2 points I would like to conclude with. One is computation. So what am I saying here? Like, of course, I'm showing the good aspects of the method, this finite sample method. Does this mean like we've been doing it wrong all this time? Like this bootstrap and base, should we forget about it? Of course not. But I would argue, and hopefully I've shown evidence for it, that if computation allows it, then you should do this finite sample. At the very least, as an aside to other methods. Okay. Why? Because it's a finite sample method. It's also unambiguous. Like it's uniquely defined. It doesn't have a million different variations. Unfortunately, the problem is that it takes a lot of computation. And here's just one kind of quantification of that complexity. So if delta is your discretization, let's say you split an interval into 100 different values, ds is your statistic dimension, b theta is your parameter dimension, then this explodes exponentially. Okay, in principle. And then C is the computation of just one single density. If that takes C time, then just bundle everything together. You see that it explodes computationally. So it's a very computationally demanding procedure. So essentially, this is what we pay. We kind of trade off this validity with computation. However, I still think that in many applications like Covid-19, where you only have 3 parameters, that finite sample validity can be crucial, right? Can be preferable. You can still do it. And I do think really, at the very least, we should teach finite sample methods to practitioners, right? Because practitioners can, in many cases, they deal with simple models. They have a couple of parameters. So they can just follow these methods instead of just doing approximations and trying to figure out what to do in these situations. And here's one final example, and I'll kind of stop with that. And this goes to the point that there are applications where there are few parameters that we care about, and we should do this finite sample method. So here's from the official Pfizer report on the COVID vaccine COVID-19 vaccine efficacy. It says, it ends with the following. I think this is towards the end of that study. It says the following, that a minimally informative beta prior, beta 0.7001021, I'm not messing up with this. This is really what they're writing. Is proposed for theta 1 minus vaccine efficacy over 2 minus vaccine efficacy. The prior is centered at bats, which can be considered pessimistic. The prior also allows considerable uncertainty. The theta is this, and the corresponding interval for vaccine efficacy is blah. So somehow this is kind of allows considerable uncertainty. I'm pretty sure there's a very good technical justification of why these numbers and these words make sense, right? But it just all seems too messy, too out of hoc. Someone has to understand what a prior is, what an informative prior is, what a beta is. What are these coefficients? Where they come from? Why do you have to make this ratio and not just look into the vaccine efficacy itself? Why do you center at this value? Why? It's just so much going on here. And the vaccine efficacy is really two numbers. One is the proportion of COVID cases, probability of COVID in the treatment arm, probability of COVID in the control arm. That's it. Just P and Q. Just two proportions. We can scan all possible values of them very easily in a couple of seconds, and you pass it through the method that is quite a simple binomial density again. Just scan all the possible combinations of these two parameters, and you get an interval that's 88.8%. Sorry, this is a mistake. This will be 98%, as 95%. That's the finite sample, and this is 4 lines of code. And you don't have to think about any prior, right? It's just brute force calculation. The official reporting in the New England Journal of Medicine was 90.3%, 97.6%, but it takes 5 PhDs to write that. So I really think that, at least in this application, clearly, I'm not arguing that this is universal method, but clearly I'm saying that there's severe limitations and mainly computation. But in these cases, especially these crucial ones where there's 1, 2, 3 parameters that we care about, we can do finite sample value. Okay, in some cases also exact. All right, that's all I had. So I'm going to spare you from the concluding remarks. Thank you for your questions and your attention.
One more question. This gets to statistics classes and teaching statistics. Do you think that these finite-sample methods, should they be part of a broader statistics education that includes normal approximation and sample methods and stuff, or should there be an entirely new class or paradigm for teaching statistics?
Yeah, that's a great question. I haven't gone into detail about the, but I do think we should teach first the finite sample approaches, and it's not only that, right? Like the plot regression is one good example where it's an exact method for estimating proportions, doing inference of proportions. I will definitely prefer teaching that first, and then perhaps the normal approximation. You don't even have to do normal approximation, to be honest. This is what you have to teach because this is the exact interval, right? There's code, you can actually code it up, you can see it. If you want to do approximations, fine, but this really should be, in my mind, it's clear what the priority is. Now, how they're going to be allocated, separate class, the same class, I'm not really sure. That would be great from a pedagogical perspective, but at least in terms of priority, I would definitely prefer teaching those finite sample methods whenever they exist.
Do you specify the density? You have to know.
You have to know the density.
Yeah. So you don't have kind of like way you kind of maybe some kind of density, some carrying out maybe that you might use.
Yeah. You could approximate the density.
Yeah.
To a kernel perhaps.
Yeah.
But then it becomes approximate. You kind of lose the finite sample value, right? Okay. Then it's however, here's something I didn't talk about is this S here. It can be just only one aspect of the data. It doesn't have to be everything, right? So in any given, suppose you have a big data problem and many things flying around. Suppose there are a couple of 1 or 2 quantities you can very easily calculate. Sample means, sample variances. you can still use them to do inference and pass it through that method, right? So whatever you can calculate easily, whatever you can, and you can also calculate the density of easily, you can still pass it through that method. So it's not that this S has to be something special. It can be any summary that you choose. Right? Of course, the better it reflects the problem, the more power you're going to have. Right? This S could be completely, let's say, unrelated with your parameters. Then your inference is going to be too conservative. So the choice of that S enters into the power considerations that I haven't talked about here. But the more general point is that this S doesn't have to be all the data. It can be aspects of the data that you can do computations on.
All right, let's thank Ponce again.
Thank you.